Okay, so before we finish with the subject, I would like to, in less than 1 hour, do this short presentation, speaking about the challenges, and then also some few curious facts that happens within the electric technology of wind turbines. Okay. Then in the second hour, you will have time to finish the coursework or whatever you want to call to ask me related to the exam or whatever. Vale. But I think as a final lecture in this subject, the best thing to do is to do like a summary in which we are going to speak about the challenges. We have been watching technology of wind turbines quite deep under detail and so on. Then we have seen the historical evolution of this technology, and now we are going to look at the future a little bit, which are the challenges that we can find within this technology. Okay, so very shortly, the presentation that I have prepared is divided in two parts. The first part, we will speak about the challenges, and then, as I said before, we will shortly say some few curiosities or curious facts in relation to this technology that maybe is not so obvious, but it's just useful to remark or to highlight them. Okay, so first of all, we will see the challenges according to my view. Probably there could be another professor, or there could be another teacher, or there could be one person, one engineer from one manufacturer that will have a different view. Obviously, this is my view, and then if you want, we can discuss. But anyway, so I often like to distinguish between the specific challenges that we can find within a specific technology, and then we can speak about the challenges that we can find in every single technology. Okay, I like to distinguish between both, and I think that in wind turbine technology, it is easy to find it. It is easy to see it. So that's why I have divided into two parts. So let's start from the specific challenges in wind turbine context, and we can say which is the challenge. What is the challenge that the development that we are watching in wind turbine technologies in the last few years or decade, 10 years more or less, or even more, and we will see it in the future as well. I think that more and more we are asking to the wind turbines to provide more services to the grid, incorporate more functionalities rather than only energy production. Which functionalities are those ones that we are increasingly demanding to the wind turbines? In operation, this is how the grid codes divide them. In operation, under normal operation conditions, we are asking frequency regulation capability, inertia control. This is not still a reality, but in some countries, they are starting to demand it. Then voltage regulation capability that comes through reactive power control. The other one is coming according to active power control. Then operation under fault conditions. More and more, the grid codes are demanding more restrictive operation, low voltage read-through and high voltage read-through. We have seen them in previous chapters. And then also another challenge that is very important and is increasingly demanding more and more and more is the minimization of harmonic emissions to the grid. wind turbines are based on power electronic converter, and power electronic converter creates voltage harmonics and therefore creates current harmonics. So those current and voltage emissions must be minimized the more we are installing wind turbines. More installation of wind turbines, more harmonic emissions. Therefore, the harmonic emissions must be reduced. Okay, this is according to my view the challenges that we can find in this technology. How can we improve this? Always by improving generators, by improving the power electronic converter or the filters, switching frequencies, better filtering, protection circuits, the crowbars and the choppers for this demand. For instance, control algorithms everywhere. And the future, probably, this is not still a reality, as I am telling you, incorporating energy storage systems in order to accomplish this challenge. Okay? And the reality is that all the services that we are demanding more and more to wind turbines are oriented to what? Why? The question is, why are we demanding that? Basically, to preserve what we call the grid voltage. All the generation systems, they create the grid voltage all together, la tensión de la red, as we call it. And we need to preserve, we need to do something in order to this voltage maintain in a constant way. So there are some quality requirements. The first one is obvious. The amplitude should be maintained during or within some margins. Okay? The other one, in a sinusoidal voltage, in the grid voltage, en la tensión de la red, is the frequency. The frequency as well should be in Europe, at least, maintained in 50 Hz or within some range. That depending on the country, maybe 0.4, 0.3, or 0.2. But that frequency cannot be modified too much. How do we control the amplitude? By means of the reactive power. How do we control the frequency? By means of the active power. Okay. Then the harmonic emission. It's obvious. If every single wind turbine or generation system based on converters is injecting harmonics, this grid voltage would not be a sinusoidal voltage, will be something different. Would be a summatory of different frequencies, which is not useful at all. That will bring problems such as power losses and so on. So that's not desirable. And finally, during faults, what we are demanding to the wind turbines is to provide current, reactive current, in order to be able to avoid the fault. Okay? And why is it that done? In order to ultimately to avoid the blackout. El efecto dominó que pudiera suceder, that could happen, and reach the blackout that nobody wants, obviously. And these are the challenges, and these are the reasons, according to my view. Maybe often there are grid codes that we need to follow, but we don't realize why is the reason why we are being asked to do that. So let's have a look one by one, all those challenges, very, very shortly. Active power control. You know that the grid must fulfill that in every single moment, the generated power and the consumed power must be equal. If this balance is not fulfilled, what happens is that the frequency goes up or down. Okay, so that's very difficult to do, and something very important to avoid this instantaneous mismatch is the inertia. The grid should have one inertia in order to don't be too weak. You know that. What happens here? The conventional generation can easily adapt to the power demand of the consumption by putting more or less coal, carbon, putting more or less gas, and so on. However, the wind, the wind that we have is the wind that the meteorology or climate imposes at this moment. So that's not something easy to do. So which is the solution for that? Little by little, if we want grid in which the wind turbines or renewables are have a very specific portion, more than 50%, this is very important. Otherwise, this is unstable, and the blackout is very easy to happen. So the solution for that is to incorporate, energy storage systems in the mismatch, in the mix of power generation. Maybe not at the turbine level, maybe there is no space to put batteries and another converter within the wind turbines, maybe something that can be located at the substation. But the future is this. The future is this, and we are watching that is starting to be demanded compulsory in some countries, such as, for instance, in Australia, which is an island, and this is a very weak grid, and UK as well. Some kind of this type of energy storage systems. So in the future, probably this will be a reality because it's a real demand. Reactive power control. Well, in order to have the capacity to have voltage regulation, the idea is very simple. All our devices, our chargers for the mobile phone or whatever, they need voltage and amplitude which has to be constant. Otherwise, they don't work. So that's why the voltage amplitude should be within some limits. This is quite simple to do with wind turbines. We only need to design the grid side converter with an exceeding amount of current prepared to give reactive current. You understand how to do it. We have seen it not only here, but in other subjects as well. This is not a real very important challenge, sorry. But in order to do efficiently and competitively between manufacturers, it's a challenge to find how much current do you have prepare for the reactive power in order to have voltage regulation capability. To do it, so the challenge is to do it in an efficient way. It is simple to do, but not so simple to do if you want to be competitive with in comparison with other companies or manufacturers. You have to do it better than the others. The other challenge was operation under fault. The grid voltage must not be interrupted. You know, if that a fault occurs at the grid, that is amazing, because the wind turbine must to forget providing all the active power that was providing in less than 10 milliseconds, in a very short period of time, has to forget about that power and must to provide the full current in a reactive way, in order to what we call in Spanish, despejar la falta. That's very challenging, and we are doing it. Thanks to that, the overcurrent is detected and the breakers are open. And that's a challenge to do, and we need to design effective protective circuits, crowbars, that are normally located somewhere in here in the power electronic converter, control algorithms like PLLs very fast and current loops very fast and accurate, and so on and so on. So that's a challenge. That has been a challenge in the last 10, 20 years, and in the future will be a challenge as well. And finally, the harmonic emission. Okay, as I said before, yes, this should be 50 Hz, but only one frequency of 50 Hz, not a summatory of 50 dominant Hertz plus an amount of harmonics due to the switching of the power electronic converter. This is not useful at all. This is not desirable. So the grid voltage must be substantially clean of harmonics. In order to do what? In order to avoid losses in cables, in the transmission cables, for instance, if there are harmonics, those produce power losses, and that's not good. Or even more, if the voltage will be corrupted or distorted by harmonics, certain loads could be operating not properly. So obviously, the grid voltage should be a sinusoidal 50 Hz voltage. And which is the challenge? To reduce more and more and more this harmonic emission as we can. Maybe in the past, only paying attention to a power electronic converter individually, but now in the future, now in the present, and probably in the future, by watching the combination of all the wind turbines, how they behave. Not only paying attention individually to each wind turbine, but rather to all the park, because there are interactions that could amplify harmonics. So you realize this is something quite curious, because what we are demanding to wind turbines is to behave as conventional generation systems. Conventional generation system has the ability to provide all the power that you want. They don't have, if we go here, sorry, they can control the frequency by providing more or less active power, by providing more coal or gas. They can control, this is not so obvious, the amplitude by means of the reactive power. Maybe this is not so obvious, but conventional generation, as they are based on a synchronous generator connected to the grid, they provide inertia as well, and they don't provide or they don't emit harmonics. And they naturally, when the voltage fault occurs, when the voltage drops, they provide short circuit current. So what we are demanding to the wind turbines is to behave as these conventional systems, which is something curious according to my view. I don't know what you think about it. And then we were speaking about the specific challenges of wind turbine technology, but there are also some challenges in all that occurs in all technologies. Well, we have seen that nowadays the dominant technology in wind turbines are these two ones. These may be for higher power in offshore, but in low power, up to 6 megawatts, maybe this more suitable. So these are nowadays the more typical configurations, technologies. And a part of the challenges that I have mentioned before, we are still having all the challenges that all technologies have. Improve performances, reduce costs, very, very important. Maybe for a manufacturer, I have seen videos and interviews of some manufacturers. They always have in their idea cost, reduce cost. Yes, it's very important. Reliability, robustness, cycles of living. One wind turbine, if can operate not 20 years, but 40 years, better. Reduce maintenance and so on. So these are the challenges that every single technology can have. And how is it made in wind turbine context? By improving generators, by improving power electronic converters, by improving protection circuits within power electronic converters, by improving control, at least from the electrical technology point of view. Everything passes, everything goes by the improvement of these elements. Okay? And as I always say, this is a multi-objective optimization process. This is a multi-objective challenge. There are many vectors pushing in different directions. Reliability, grid codes, reduce the efficiency, increase the power, reduce the complexity, reduce volume, and so on and so on. Many vectors of different nature pushing in different directions. And depending on the manufacturer, they can find different equilibriums, providing different weights or different priorities to those different challenges or vectors or objectives, individual objectives. Do you see the idea? More or less. Okay, so those were the challenges. I don't know if you agree or not. Some few curious facts, not very important, but just to emphasize them, maybe you didn't realize. 3-blade system, maximum power extraction. You know that normally we have power curves like this of different manufacturers, and this is the CP in function of the wind speed of different manufacturers. This is something equivalent for a wind turbine of Siemens Gamesa of 5 megawatts, the one that is going to be installed in Arcamo, in Álava. But if you realize, you know, the occurrence of the wind, normally we estimate or we model it with a wave distribution. And for this wind turbine, normally it's fine that we have a 7 meters per second of medium or average wind speed. So the most likely, if we correlate this statistic distribution and the power, we have this. So we are always saying we have a wind turbine of 5 megawatts. 5 megawatts is somewhere here. So the probability of occurrence is less. So if this is correct, because this is statistics, then the reality, we don't really know what happens. We need to measure during years what is the reality of the wind that we have. But this is something that manufacturers normally don't give you, or at least I didn't see, never. So the reality is that this wind turbine, which is called 5 megawatts wind turbine, is going, the majority of the time, is going to be working in these powers. Sin más. I'm just saying that. And if you model the location of the place like this, but the reality is that maybe instead of having 7 meters per second, we have, for instance, 4 meters per second or something less, obviously, it's obvious, the energy flow in 1 year is going to be much less. Or in the other way around, if we, instead of having 7 meters per second, for instance, we have, I don't know, 10 meters per second, so the majority of the power, the majority of the time is going to be at 5 megawatts, okay? But the curious fact here is that here we are controlling the pitch, and we are doing the wind turbine less efficient. So we are doing the wind turbine less efficient in order to capture the power. So it's quite curious. I mean, just emphasize this fact that probably you knew it. Okay, you see what I mean? ¿Se entiende, más o menos? That's a typical question that make me pupil in the streets or that is not expert on this type of things. And how much power is providing and how much time is the wind providing so statistically, we use this type of modeling with good distribution. Bueno, from the point of view of the control, for me, this, I have told you this several times, for me, this is amazing. We are controlling AC machines, AC generators that demand AC voltages and AC currents of different amplitudes and different frequencies, but we create a control that understands or controls the machine in DC. So we are controlling a machine that is operating in AC as if it was a DC machine. That's amazing. That's quite curious, no? ¿No os parece? And there are historical reasons, because at the beginning, when this was developed in 1970, more or less, in Germany, I don't know if you remember, by Siemens and some other manufacturers, the dominant regulator was the PA regulator. Or said in other words, the resonant regulator was not invented yet. So the people who was in charge of controlling AC machines, they thought in such a way to control the machine by using the regulators that they knew, the PA regulators. That in DC, they can provide you zero error at the steady state. Then 20 years ago, later, maybe in 1990s, more or less, the resonant regulators were invented by Graham Holmes and some other teachers from the university. But the reality is that the inertia of the engineers is so high that we are still using this way of controlling the machines. We don't want to change to resonant regulators. And we are still controlling the machines as if they were DC machines. Nada. it's quite curious as well. Finally, we need to apply the generators or the machines. They demand AC voltages of different amplitudes and different frequencies, but AC, sinusoidal. But the reality is that we are supplying nowadays these AC machines, in this case generators, by power electronic converters. And those power electronic converters, they do not create pure sinusoidal voltages. The reality is that they create from DC voltages something which can be similar to an AC voltage. But the standard and the most extended ones is the 2-level waveforms, 3-level waveforms, 5-level waveforms, and so on. Or here you have a picture. The bigger levels that you have, the similarity to the sinusoidal voltages is bigger. But at the end, we are supplying AC machines with DC voltages. DC voltages of different amplitude that are switching very high frequency, and the machine interprets these voltages as if they were AC, dominant harmonics. Pero no deja ser curioso, ¿no? Okay. And okay, in order to do that, we have different power electronic converters. And the reality in the future maybe is not going this direction. Probably both directions will be open, but with the silicon carbide semiconductors, the wide band gap semiconductors, the tendency is to switch to higher frequencies. So probably this will be enough. This converter topology will be enough. So probably some manufacturers will go with these new semiconductors in these directions, and maybe some others will go in these other directions. But the future is not so clear. Okay. We in our university, there is one group that is working very actively in partial power conversion. Just check that you know that in order to create one, in order to control the total power, we can use the total power electronic converter or the partial power, more or less 30%. At the beginning, nobody believes in this way to do the things, but after more than 20 years of installation of thousands and thousands of wind turbines like this is a reality, and everybody is, todo el mundo cree que es buena. So this partial power converter system, the fact of using a power conversion of less power than the total power of the system, 10, 20, 30%, is becoming a reality in some other applications. I don't know if you have been told about that, but especially in DC-DC, in batteries and energy storage systems, there are some power converter configuration very suitable that can be done something very similar to this. And again, the pioneers of the technology that firstly introduced this concept, this revolutionary concept that nowadays is very obvious, but at the beginning it was revolutionary, was in wind turbines, partial power conversion. Simple. So this was all the presentation. No sé si tenéis alguna duda, alguna pregunta, alguna aportación.